Hello. Good morning, everybody. Welcome to this third day of the FOCM conference. My name is Elena Celedoni, and I'm going to chair this session and introduce the first speaker today. Melvin Leoch did his PhD finished his PhD in 2004 at Caltech under the supervision of Jerry Marsden. Then he moved to the University of Michigan and to Purdue, and then he moved to the University of California, San Diego. He is now a professor of mathematics there, and Melvin Leoch did important contributions in the field of geometric and computational mechanics and geometric numerical integration. Today he's going to talk about variational discretizations of gauge field theories using group-equivariant interpolation. Please.
Right. Thank you, Elena. So I'd like to thank the organizers for the invitation to speak here, so it's a great pleasure. So this is a joint work with Evan Golick, who's here. It's like, as well as a former student, James Hall, and a former postdoc, Joris Vanke Schaefer, and very generously funded by the National Science Foundation. So let me try to motivate what this is all about. And the main motivation is this application to general relativity. All right. So in recent years, there's been a lot of interest in numerical relativity because of this phenomena. It's like which was first predicted by Einstein. It's like back in 1916, which was gravitational waves. And the idea is that when you have two massive, it's like objects like black holes, and they coalesce, they will end up causing ripples. It's like in space-time, and you would be able to, in principle, detect these ripples. And so the experiment, it's like which aimed to discover these gravitational waves, is what is known as the LIGO project, which is this laser interferometry gravitational observatory. This was a joint project between Caltech and MIT. And back in September 14, 2015, they discovered the first signatures of gravitational waves. All right. So where does numerical relativity fall into this? So the basic idea was that when LIGO was first developed, the signal-to-noise ratio was such that you wouldn't expect to actually see the signals clearly, and you would have to basically do some sort of correlation analysis with a reference waveform in order to see whether or not this was somehow embedded in the gravitational wave signatures. So this is where relativity, it's like came into, numerical relativity, it's like came into play here. All right, so let me try to say a little bit about how you formulate this. So the Einstein equations of numerical relativity, it's like can be formulated in a Lagrangian or variational setting. It's like using what is known as the Einstein-Hilbert action, and it's defined in the space of Lorentzian metrics. Okay, so it's given by this expression here, where you have the Ricci curvature, and it's like, and this is a Lagrangian associated with matter. And you can write down the Einstein field equations, which is given as follows. And the basic setting for this is that this is a second order field theory in the sense that it involves essentially second derivatives of the data, which is the Lorentzian metrics. And it's a gauge field theory, which basically means that there are certain local symmetries of the problem. And those local symmetries are associated with the fact that on a space-time manifold, you can reparameterize the space-time manifold without changing the physics of the problem. All right, so what are the more general setting for this is, so this is in the context of gauge field theories. So a gauge symmetry, as I sort of alluded to before, is a continuous symmetry, but the idea is that at every point in space-time, there's a different element of the symmetry group, if you will, and that element of the symmetry group basically sort of varies continuously, if you will. And under those transformations, the physics of the problem stays invariant. Okay? So the consequences of a gauge symmetry in the problem is that when you look at the corresponding Lagrange equations, they're in some sense underdetermined. Okay? So the evolution equations themselves are insufficient to propagate all the fields. And one way to think about this is that the gauge symmetry results in the Euler-Lagrange equations being functionally dependent. And so they don't give you, it's like sufficient independent equations of motion. So this basically causes the fields to be decomposed into two types of fields, one of which are known as kinematic fields, and these have no physical significance. They really correspond to just these gauge degrees of freedom. And then there are the dynamic fields and the conjugate momenta, which actually have physical significance. Okay? There's also a sense in which the equations are overdetermined when you try to formulate this as an initial value problem where you specify data on a sort of space-like Cauchy surface, then you don't have freedom to arbitrarily specify that data. Okay? So it has to satisfy some sort of constraint on the initial data, and this kind of constraint is usually sort of an elliptic type PDE. So the way it's like I propose to approach this is that I'm going to approach this using this notion of multi-Dirac mechanics in geometry, and it's a generalization of Lagrangian Hamiltonian mechanics, which is in some sense well suited to problems with degeneracy. And I guess the point is that when you have symmetries, they also lead to degenerate systems. Okay? Whoops. All right. So let me sort of make things a little bit clearer. It's like perhaps with an example which is a little bit closer to what you might have seen before. So let's just look at electromagnetism. And so these E fields and B fields are electric field and magnetic fields respectively. And you can write down Maxwell's equations. It's like in terms of the scale and vector potentials as follows. All right? And you can easily check that these equations are invariant under the following transformations of the scale and vector potentials. All right? So this is an example. It's like of a gauge symmetry. It's like the implications of this gauge symmetry are that you can't arbitrarily specify the initial data on a Cauchy surface, but they have to satisfy these kind of constraints. All right? So as a practical matter, it's like most of the time what people do is that how do you deal with the fact that you don't have enough equations to evolve this is that you choose what is known as a gauge condition. So you fix a gauge. All right? And so some possible examples of gauges in electromagnetism are the Lorentz gauge, given as follows, and the Coulomb gauge. And the problem, if you will, it's like if you've done any analysis on this, is that if you choose the right gauge, then things are somehow easy. And the choice of the gauge is in some sense dependent on the kind of solutions you're looking for. All right? So there's no real systematic way of deciding which gauge to use for a given problem. And as a numerical analyst, one of the questions really is that if you actually have a problem where you actually need to do computation on it, then it's not so clear that even sort of a global choice of gauge is appropriate. If you have a problem with sufficient complexity in the solutions, maybe a global choice of gauge isn't the right thing to do. So really, how do you deal with sort of this gauge invariance? How do you choose gauges? Is really something which I think bears further thought in the context of numerics. Okay. So one of the other consequences of symmetries are what is known as Noether's theorem. So what happens is that if you have a continuous symmetry of the action, then there's an associated quantity which is conserved in time. And the simplest example of this is that comes from mechanics. And basically, if you have a Lagrangian or Hamiltonian which is time invariant, then there's an associated Noether quantity which turns out to be the energy. Okay, so if you have a time-independent Lagrangian or Hamiltonian system, then the energy is a constant of motion. All right. And in the case of gauge field theories, there's a similar idea that if you have this gauge symmetry of the action, then there's what is known as a Noether current, which satisfies some sort of continuity equation. And then when you integrate this Noether current over a space-like surface, then there's a continuous quantity known as a Noether charge, which is preserved if you have the appropriate boundary conditions. So in the case of electromagnetism, these are the Noether currents. And so going back to the example for general relativity, it's like the Einstein-Hilbert action for general relativity. It's like has as its Noether quantity the stress-energy tensor given as follows. And this is the Noether charge associated with space-time diffeomorphism symmetries. All right? Okay, so what are the consequences of gauge invariance back in the context of general relativity? Okay, so as I sort of alluded to, because of Noether's second theorem, the Euler-Lagrange equations are not independent, and so only 6 of the 10 components of the Einstein equations are independent. Okay, and so in order to compensate for the fact that you only have 6 independent sort of equations, you have to impose, or you typically impose, a gauge. All right, and so there are these gauge conditions. And there's what is known as the maximal slicing gauge, as well as the harmonic or the Donder gauge. And so the one which is oftentimes thought to be relevant, it's like for gravitational waves, is the Donda gauge, it's like, which is Lorentz invariant, yeah, it's sort of nice for gravitational waves. So, and when you formulate this as an initial value problem, as I said, the Cauchy data is constrained, and so in particular, the Cauchy data has to satisfy this Gauss-Codazzi equation. And if you think of it as a variational problem, then the problem is what is known as degenerate, which is to say that the Legendre transform associated with this is not invertible. Okay. All right. So that's sort of just some properties. It's like of general relativity. It's like which is a consequence of this sort of general covariance. It's like of the equations. And now let's talk about what this means. It's like from the point of view of numerics. Okay. So because of the problem is sort of space-time covariant. What you would like, or what we would like to avoid, is to have space-time meshes which are just tensor product meshes of space-time. And the reason is because that constrains the topology of solutions which you're allowed to have. Okay. So what we're proposing basically is to develop a framework which really sort of is predicated on some sort of simplicial, unstructured mesh in space-time, and then we want to deal with the fact that you have degenerate problems, and so we claim that this notion of multi-Dirac mechanics, which I will talk about a little bit more, and the associated Hamilton-Pontryagin variational principle for field theories, this is well adapted to degenerate field theories. Then finally, the other thing we would like to do is this fact that the Nova theorems they play such an essential role. It's like in the dynamics of sort of these gauge field theories, that we would like to have a discretization which respects that gauge or the symmetries and the associated conservation laws. Okay, and so the way we propose to do this is that there are what are known as variational integrators, which I'll talk a little bit more about. And variational integrators have the property that if you discretize the action in a good way, then there's an associated discrete momentum conservation law. And the way you go about constructing discretizations which are good in this sense involves the use of gauge invariant discretizations of the function spaces. So that will be at the end of the talk. All right. So the mathematical setting, it's like which we're proposing to use, is what is known as Dirac geometry and mechanics, and it's a generalization. Dirac geometry is a generalization of what sort of commonly seen geometric structures. It's like in mechanics, it's like symplectic and Poisson manifolds, and in some sense, it encompasses both symplectic and Poisson structures. But in addition to that, allows you to understand what it means to do Legendre transforms. It's like when the Legendre transforms are degenerate, and it allows you to deal with interconnected systems, non-holonomic systems, and so on. So it's a very, very general mathematical setting. And then there's an associated variational principle to this, and this is what is known as the Hamilton-Pontryagin principle. And it unifies, amongst other things, it's like Hamilton's principle, Hamilton's phase-space principle, as well as this Lagrange-Lambert principle, which is relevant for non-holonomic mechanics. So let me try to look at the simplest case, which is just the usual mechanical situation. So this is defined on what is known as the Pontryagin bundle. You should think of it as just positions, velocities, and momenta. So this is in contrast to usual Hamilton's principle, which is defined in terms of positions and velocities, or Hamilton's phase-space principle, which is defined in positions and momentum. So the aim is to combine both of these variational principles into one. Okay? So the form of this is that you have a Lagrangian, which is typically kinetic minus potential energy in the case of mechanics, and you relax the second order curve condition. Normally, it's like Hamilton's principle states that you have L as a function of Q and Q dot. All right, so you're going to relax the condition that the positions, velocities are related by a time derivative. And so you think of V now as an independent variable, but then you impose the condition that V is equal to Q dot. It's like via Lagrange multiplier. And I have sort of intentionally chosen to label my Lagrange multiplier by P. It's like because, as it turns out, the Lagrange multiplier is going to have the interpretation of the momentum. All right, so it's sort of obvious just by, it's like the theory of Lagrange multipliers that this is equivalent to the usual Hamilton's principle. Okay, so let's just see what happens when you look at the variational equations. So when you take variations and you compute those variations using the usual integration by parts kind of argument, you end up with this form of the variation of the action integral, all right? And if you require that this is stationary, then you get what are known as the implicit Euler-Lagrange equations, which are given here, all right? So it's easy to see that if you combine all these things, that you get the usual Euler-Lagrange equations, because it's like P is dl dq dot, all right? So d dt dl dq dot is equal to dl dq, which is the usual Euler-Lagrange equations. All right, so you might say, well, it's like, what's the benefit of using this as opposed to the usual Euler-Lagrange equations? The usual Euler-Lagrange equations are second-order differential equations when the Lagrangian is non-degenerate. The problem is that if the Lagrangian is degenerate, and the simplest case is when you have in the mass matrix is not full rank, so there are a bunch of terms where, imagine you have a mechanical system where some of the objects in the mechanical system have zero mass. Then essentially what happens then is that for parts of the Euler-Lagrange equations, it degenerates into a first-order equation, and then you don't have enough equations to evolve this forward, okay? But the way you can get around that is that this condition, the definition of the Legendre transform, essentially becomes a constraint equation. So this is what is known as the primary constraint condition. And this condition, all right, in the case of non-degenerate equations, allows you to have enough equations to actually evolve the problem forward, okay? So in the non-degenerate case, it's like, you can just sort of simplify everything by eliminating the definition of the momentum. But in the degenerate case, then this condition is like, turns out to be important. All right, so this is sort of the intuition as to why you might want to use this formulation as opposed to the more sort of standard sort of Hamilton's principle when you're studying problems with degeneracy, okay? And in particular, any problem with symmetry is going to be degenerate in some appropriate sense. All right, so that's in the case of mechanics. Let's say how you can generalize this. How do you generalize this to sort of the problem of field theories? Okay, so this is in the category of multisymplectic geometry. So the thing you have at the bottom here, you should think of as space-time, and then you have the fields over it as a fiber. It's like over this space-time manifold, and then if you have a solution of a PDE, it corresponds to a section of this fiber bundle, which more or less says that for every point in the space-time domain, you associate it to something which is space-time point, comma, the field value at that point, right? So this is, if you will, this potential space, it's like for which it's like the solutions take their values. So you have this space, it's like which is n+1 space-time. You have a configuration bundle, which are, again, these fields over space-time. And then you have a configuration which is a map from space-time to this space-time comma fields space. Then what you need to do is you need to define, it's like what is known as a Lagrangian density. So the usual Lagrangian is defined on positions and velocities. The analog of this in the field theoretic setting, at least in the case of first-order field theories, is what is known as the first jet bundle. All right, so you take the first partial derivatives of the fields with respect to all the space-time variables. All right, and then once you have that, you can introduce what is known as a Lagrangian density, which is a map from this first jet bundle, it's like to n+1 differential forms on the base space. And so essentially what happens is that once you have this object, you can define some domain in the space-time point. You can integrate this n+1 differential form over that space-time domain to then give you an action, basically. Okay, so this is what we're doing here. And that defines an action integral, and then Hamilton's principle states that the action is stationary with respect to sort of fixed data, fixed boundary data. Okay, so that's the setting, and you can then do the same kind of trick we did before. You can generalize Hamilton's principles of field theories to this Hamilton-Pontryagin principle, and it's the same kind of argument. Now you have the base points, the field values, and then these are, the first partial derivatives. But here it's like, I've again relaxed the condition that the first partial derivative, that these sort of jet variables are the first partials of the fields with respect to the space-time points, right? So this is thinking of V instead of Q dot, if you will, and then this is the condition, the analogous condition that q dot is equal to v, all right? So that's the analog. And then you have this Lagrange multiplier, which is going to be what is known as a multi-momentum, okay? And you get these implicit Euler Lagrange equations. So one nice thing about this covariant formulation is that you might recall that energy and momentum are not really independent of each other. It's like in a fully covariant setting. And this is reflected by the fact that when you take the Legendre transform of this problem, you include both the usual momenta as well as this term here, which, if you look at it, is really just a definition of the energy. Okay? All right. There's also a sense in which there's an associated multi-Dirac structure. And here, before I get into the details, it's like, let me just sort of say that if you have a symplectic form, in the mechanics case, so a symplectic 2 form, and you think of the map from a vector to the contraction of that vector by that, the contraction of the symplectic form by that vector, you have a map from vectors to covectors, and you think of the graph of that map, then that turns out to be what is known as a Dirac structure, okay? And so more or less, this is the multisymplectic generalization of this idea that given a symplectic form or multisymplectic form, the graph of this multisymplectic form in some appropriate sense induces what is known as a Dirac structure, okay? So this is the canonical n+2 multisymplectic form. It's a generalization of symplectic structures to this field theoretic setting, and then you're essentially looking at this graph of this map here. And the reason to do this is that then this allows you to write down the Euler Lagrange equations as well as Hamilton's equations in this way here, okay? All right. So, all right. So let me talk about what happens when you try to do numerics and all of this and what our approach is, okay? So we have these geometric integrators, and there's an entire workshop. It's like at this conference on that. And the basic idea, it's like behind geometric integrators, is that you would like to construct numerical methods which respect the invariances. It's like sort of geometric invariance of the solutions of certain sorts of differential equations, and you would like the numerics to respect that kind of property. Okay, so basically, in our context, it's like the gauge symmetries really play a very, very fundamental role. It's like in the Einstein equations. And there are these associated conservation laws, which, if you will, it's like can be interpreted as why the Euler Lagrange equations are not independent of each other. So the goal then is to construct discretizations which respect and preserve these properties. And so we propose to use geometric integrators, which basically are class and numerical methods that preserve geometric properties such as symplecticity, momentum maps, or if the dynamics themselves evolve in some sort of nonlinear manifold, be they some sort of Lie group or homogeneous space, you might want to develop methods which preserve that as well. And the intuition, if you will, for why these are sort of oftentimes good ways of approaching the problem is that they give you sort of longer, sort of better long time, it's like numerical stability, and better qualitative agreement, it's like with the exact flow. All right. So now I'm going to talk about the specific approach we're taking. It's like to discretize this problem, which is what is known as a variational integrator. And the basic idea behind a variational integrator is to try to discretize Hamilton's principle. So in Hamilton's principle, you have, imagine the initial and final points, it's like of a trajectory. And Hamilton's principle states that the trajectory which connects these 2 points is that which extremizes what is known as the action integral, which is the integral of kinetic minus potential energy in the case of mechanics. And so one way to discretize this is to imagine that instead of having a continuous curve, it's like you sample those points, and then in place of the action integral, we introduce what is known as a discrete Lagrangian. And the discrete Lagrangian is supposed to approximate the following object, which we call the exact discrete Lagrangian. And it's basically the action integral over a short time interval, okay, evaluated along a curve which satisfies the Euler-Lagrange boundary value problem. So it satisfies, so if you evaluate this discrete Lagrangian on the point q0, q1, you want it to approximate this action integral over the curve q01, where the curve q01 satisfies the boundary conditions as well as the Euler-Lagrange equations over that time interval, okay? So this turns out to be related to Jacobi solution of the Hamilton-Jacobi equation. This is the exact generating function which generates the flow of a Hamiltonian system. So of course, this is kind of a chicken and egg thing. You can't actually compute that because in order to compute this, you need to exactly solve Hamilton's equations or the Lagrange equations. And if you could do that, then you should just stop there and not bother, right? So, but nevertheless, this is still useful because it tells you what you're aiming for, and it then sets up a framework when you can do mathematical analysis. All right. So before I do that, let me say how that generating function leads to equations of motion or discrete equations of motion. So the way you do this is that this discrete Lagrangian, as I said, can be thought of as a piece of the action integral over a small time step. So if you imagine summing that up over the entire sequence, you get an approximation of the action integral over the full interval. Okay? So this is what's here. And then if you take variations of this and require that it's stationary, then you get a discrete version of Hamilton's principle. And you can write down the stationarity conditions for this. Then this gives you what are known as the discrete or Lagrange equations. You can think of it as a two-step method. It's like on Q, all right? And if you don't like to think of it that way, you can introduce, it's like momentum variables, and then you get these set of equations, which are equivalent to the first set of equations when you eliminate the momentum variables, all right? And if you know something about symplectic maps, then it should be clear that this is essentially just a characterization of a type 1 generating function, a symplectic map in terms of a type 1 generating function, which is this discrete Lagrangian, okay? All right, so this framework has been used. It's like in a variety of problems. This is some stuff which I had done with a former student of mine, Tiang Li, who's now at George Washington, mainly sort of applications to multi-body systems, mechanical systems. This is supposed to be a multi-body system in a perfect fluid. And then Todd Murphy, it's like at Northwestern, has been instrumental in sort of extending these methods to really large-scale multi-body systems. And one of the goals is like which we have, it's like in a joint proposal of ours, is to develop a rational framework to construct variational integrators in a systematic way by basically combining, it's like integrators for smaller subsystems, all right? So this is basically what he's applied it to. And then there, of course, it's like PDE generalizations. It's like, and amongst other people, it's like Eitan Greenspan at Columbia. It's like has been using sort of methods which are at least motivated by this in the context of various. It's like elasticity and plasticity calculations. This is cloth. It's like being pulled off something. It's not so obvious. And then this is sort of an attempt to understand the dynamics of what happens when you tie a string with some intrinsic curvature to it. All right. So that's to show you that you can actually use these methods on interesting practical problems. And then this is really about why it's interesting from a analysis framework. So the first of which is that there's this discrete version of Noether's theorem. And Noether's theorem, as I said, relates symmetries. It's like of a variational problem with the associated conservation laws. So the notion of symmetry in this problem then is that if you have this discrete Lagrangian, which is a scalar value function on two copies of the position, then you want that this discrete Lagrangian transform in the right way. So the appropriate notion of a group acting, it's like on Q cross Q, is basically just a diagonal action. So you have, say, points Q0 and Q1, and they both are acted, say, on the left or the right by some group element. And if the Lagrangian is invariant under this diagonal action, then there's an associated momentum map, which is given by this expression, which is preserved by the discrete flow. So there's this discrete notion that symmetries of the discretization correspond to conservation laws, all right? So if you're paying attention, it's like then the thing, it's like, bless you, the thing that's like which you should keep in mind is that I haven't told you how to actually construct one of these discrete Lagrangians in such a way that it has this kind of G-invariance property, but we'll get to that. So the other thing has to do with error analysis. So I already talked about this idea of an exact discrete Lagrangian. And so the exact discrete Lagrangian generates a time h sampling of the exact flow, okay? So you have something which is, which is in principle describing the discrete one-step map, it's like what you're trying to approximate. So you can ask to what extent, okay, instead of working at the level of numerical methods, can you work at the level of the generating function of the discrete Lagrangian? Okay, so this is what this variational error analysis framework does for you. It basically says that if you analyze the error properties of this discrete Lagrangian, which is a scalar value function of q cross q, all right? And you can see to what extent it approximates the exact discrete Lagrangian. So there's an implicit time step in all these, which is h. So if it approximates the exact discrete Lagrangian to a certain order of accuracy, then the corresponding numerical method, which both of these things generate, differ by this order r. Okay, so what it does for you is that instead of directly analyzing the numerical method, you can just analyze the scalar valued function. Oftentimes that is easier. Okay, so let me give you a sense as to where this result comes from. So it comes from these discrete Legendre transforms. So it's a map from q cross q to t star q. All right, so the usual Legendre transform is a map from the tangent bundle, positions, velocities, positions, and momenta. All right, and so in the discrete mechanics framework, you typically replace, positions and velocities with two copies of position. Okay, and these are the definitions of these plus and minus discrete Legendre transformations, and it has to do with the fact that, if you think of q cross q as a bundle over q, there are two ways to think of that as a bundle, and one of which has to do with thinking of the first coordinate versus the second coordinate as the fiber variable. Okay, so this leads to two different notions of Legendre transforms. It doesn't really matter. It still defines the same kind of symplectic structure. It's like on q cross q. But anyway, it's like, so you have these two maps, and if you just sort of plot what these maps do for you, you'll see that they map, it's like this sequence, it's like which has to do with pairs of points in Q and points in the cotangent bundle. They're mapped in the following way. And then it's easy to see that the one-step method, which the Lagrange equations are basically defining, okay, which is this map up here, can be expressed in terms of the composition of these Legendre transforms in the following way. Okay, so the intuition, if you will, is that if you have if you had in this diagram the exact discrete Lagrangian, then this map here would be basically the exact time h flow map of the Lagrange equations. And if the discrete Lagrangian, the computable discrete Lagrangian, the exact discrete Lagrangian differ by some order of accuracy, then the fiber derivatives differ by the same order of accuracy. And then you can use sort of like a inverse function type of argument to say that the inverses are related to the same order, and then you compose this. And so that's basically where the result comes from, is just a sort of Cathal application of the inverse function theorem. All right, so now it's like, let me try to talk about how you actually go about constructing one of these objects. All right, so you have this expression. So this is an alternative characterization of the exact discrete Lagrangian, and it's characterized variationally. So basically it says the following. So if you take this action integral and you extremize it over the class of curves which satisfy the boundary conditions and which have enough regularity, then you get this exact discrete Lagrangian. Okay, and it's easy to see that this is equivalent to the previous definition because the stationarity conditions for this are exactly just the Lagrange equations. So the extremum of this is obtained by evaluating this integral. It's like on a solution of Lagrange equations satisfying the boundary conditions, which is exactly what I said it was before. Okay, but this then leads to a class of integrators known as Ritz discrete Lagrangians, and the idea is as follows: that, okay, you can't really compute this object, but what you can do is that you can replace the space of Tyson differentiable curves with some finite dimensional function space, and you can replace the integral with some quadrature formula. And in so doing, it's like you end up with an expression which you can then compute, all right? So the question then is that you have these two pieces of data which are used to construct the approximation, which is the quadrature rule and the finite dimensional function space. So is there a sense that the discrete Lagrangian you construct by making these kind of approximations, is there a sense that you can determine the order properties of this discrete Lagrangian in terms of this data? So that's what we're going to do. All right. So if you have a Ritz method, it's like where you choose a finite dimensional function space, then ideally it's like you should have some sort of optimal rate of convergence in the following sense: that if you have the exact solution Q and the sort of the difference, it's like between the exact solution and the numerical solution, should be bounded ideally by some constant times the best approximation error, which is the error you make by replacing, or the minimum error you make by replacing the exact solution by something it's like in the finite dimensional function space. So if you can If you can do this, it's like then what basically that means is that you can relate the error properties of your numerical method with the best approximation errors of the finite dimensional function space, so that reduces the problem of constructing a good numerical method to an approximation theoretic issue. All right? So in the case of these Ritz variational integrators, imagine what happens where you have a sequence, it's like of nested finite dimensional function spaces, it's like which in some appropriate sense, it's like limit to the space of twice differentiable curves, all right? And then you have a correspondingly sort of increasingly accurate sequence of quadrature rules, all right? Then you want to prove that the, it's like the sort of the sequence of discrete Lagrangians, it's like which you construct by choosing the sequence of approximation spaces and quadrature rules, converges in some appropriate sense to this limiting discrete Lagrangian, which turns out to be exact discrete Lagrangian. Okay, so the problem, of course, is that this involves this extremum. If it was a minimum, then this would correspond to gamma convergence, all right? So because you're looking at a sequence of sort of variational problems which limit in some appropriate sense to a limiting variational problem, and you want to ask to what extent it's like the minima of, each of those terms, it's like converges, it's like to the minima of the limiting variational problem. So this is really gamma convergence. Okay, so what you basically need to do here is to, in addition to proving gamma convergence, you actually need to show that the rate of gamma convergence is related to this best approximation error. Okay, so that's basically what the framework is. And people have done some work on this. It's like there was a paper by Michael Ortiz, it's like, and Stefan Mueller, it's like about gamma convergence of variational integrators. And there are some technical assumptions it's like you need to make. The first two of these are sort of fairly standard. The third one is a little bit less trivial, which is that the discrete and continuous trajectories have to minimize as opposed to just extremizing their actions, okay? And under those hypotheses, it's like one can check by refining, it's like this approach of sort of Ortiz and Mueller, that the Ritz discrete Lagrangians have the same approximation properties as the best approximation error of the approximation spaces, okay, for suitably accurate quadrature rules, all right? So the critical assumption is this action minimization term, this third thing here, and then you can show that for Lagrangians of this canonical form, kinetic minus potential energy with quadratic kinetic energy term, and for sufficiently small time steps, then this assumption holds. Okay, so what that basically tells you then is that these Ritz variational integrators are order optimal, and that you can have spectral variational integrators where instead of doing refinement at the time step, you do refinement in terms of increasing the, say, the polynomial degree, it's like of the approximation spaces you use, but for fixed time intervals, those things will converge, it's like at a geometric rate. Okay, so you can see this, it's like at the level of the numerics. So this is the Kepler 2 problem, two-body problem. It's like with eccentricity 0.6, and you see that it has sort of the kind of convergence rates you expect. The main point basically is that this allows you to guarantee that you can get arbitrarily high-order accurate methods, okay, using this framework. You can also do this, it's like for this p-refinement strategy. And here what's interesting is that, so what this plot represents is the fact that the error rates are different depending on whether you look at the solutions at multiples of the time step versus the solution in the interior, right? So in this construction for the Ritz integrators, you've chosen a distinguished element of the finite dimensional function space in order to construct the discrete Lagrangian. But you can ask whether this distinguished element of the finite dimensional function space is itself a reasonable approximation of the solution trajectory in the interior of the time step, okay? And so so there are two rates of convergence. There's this line and this line. So this is half the slope of this first line, okay? And what the second line represents is the error rates, it's like for the solutions in the interior of the time step, okay? And what you basically see is that if you use Chebyshev points, it takes really quite a number of Chebyshev points before it's like the errors are small enough that you can really see the effect of the errors in the interior. But the interior solution does converge at a slower rate versus the solutions at multiples of H, okay? All right. So these spectral integrators allow you to do sort of amusing things. All right. So this is a solar system simulation, and so this is the full ephemeris, if you will. It's like it's based on this JPL solar system dynamics, and then this is sort of the mathematical toy model of it, right? So what's interesting about this simulation is the following, that I've taken a time step of 100 days, which is larger than the fastest orbital period which is resolved in the problem, which is that of Mercury. Mercury, I think, has an orbital period of about 80 days. So you've taken a time step which is larger than one orbital period. It's like of an object there. Nevertheless, it's like this does reasonably well. Okay, it doesn't give you absolute garbage. And you might ask why. And the reason why, if you will, is exactly this fact that the interior solutions which you get from these Ritz curves actually are a good approximation of the trajectory. Okay, they don't converge as fast, but nevertheless, it's like they do converge. And so, so this really allows you to take steps which are much larger than the orbital periods. And the same is true when you do the outer solar system. So here now, I've taken time steps of 5 years, okay, which is again larger than the fastest orbital period, which is resolved in this. And nevertheless, you get things which are stable. Okay, you can see this. It's like in the context of sort of rigid body dynamics. So this is what's known as a 3D pendulum. It's basically a rigid body with a center of mass which is sort of not at the same point as the pivot point. All right, and here you might notice that these little blobs, as well as thin lines connecting them, the blobs have to do with basically the trajectories or the points. It's like at multiples of the time step. So these are things which in principle normally come out at variational integrator. But the sort of the thin lines are really the interpolating curves which come from the Ritz construction. Okay, so as you'll see that they actually do a fairly reasonable job. It's like of sort of smoothly interpolating it's like the trajectories. And so, so again here you can take extremely large time steps, and the main obstruction, if you will, it's like in terms of the time step restriction, is the fact that when you have rotations which are almost pi rotations, then the coordinate charts which are used to define this, it's like become nearly singular, so the numerics, it's like becomes ill-conditioned, okay? But nevertheless, it still does very well right up to that stability limit. Okay, so this is again the free rigid body, and this is just meant to illustrate the role in which sort of preservation of invariance, it's like plays, it's like in sort of numerics. And the basic idea here is that with the free rigid body, there are two variants, one of which is that the norm of the body angular momentum is fixed, and the second of which is that the energy is preserved, okay? So basically what that means is that the dynamics of the free rigid body viewed in this body, it's like angular momentum representation, is the intersection of what is known as the momentum sphere, okay, and the energy ellipsoid. So the level set of the energy is an ellipsoid, and you can see that, it's like if you try to use explicit Euler, it's like for this numerics, you'll see that it drifts off the angular momentum sphere, it's like which suggests that the angular momentum is not preserved, and you get sort of garbage. And if you did ODE 45 and you really sort of made the tolerances very, very tight, it does much better, but nevertheless you still see the slow drift. Whereas if you use one of these Lie group variational integrators, which respect the Lie group structure of the problem, as well as having this variational property, then they sort of work really, really nicely. Okay, so this is just to give you some sense as to why in some problems, particularly where the invariants play an important role, you might want to use geometric methods. Okay, you can do this for wave equations, all right? I don't really want to spend much time on that. So let me say something, so let me go back to the PD problem, which is sort of what we're aiming for. And the basic idea is that you have these definitions of generating function, or symplectic maps in terms of generating functions. And so this is in terms of the discrete Lagrangian, which is type 1 generating function. This is in terms of discrete Hamiltonian, which is type 2 generating function. So the basic idea is that symplecticity is a trivial consequence of the fact that you can write down maps like this, because all you have to do is to take the second exterior derivative of the discrete Lagrangian, and then a simple calculation shows that you get an expression like this, which is essentially just the difference of the symplectic form evaluated at two different times, right? So this basic, and of course, d squared is 0, so this basically says that the pullback of the symplectic form by the flow map is constant. All right, so the question is, how do you generalize it's like this formulation of in terms of the PD problem? So we have this sort of this exact discrete Lagrangian from before, and we would like to introduce what is known as a boundary Lagrangian, which is going to play the role of the exact generating function, but in the multisymplectic setting, okay? So it's sort of the obvious thing, it's like in retrospect, which is that in order to define a boundary Lagrangian, which generates this multisymplectic relationship, you have to specify the boundary data on the boundary of a space-time domain. So in the mechanics problem, I have a time interval, it's like, it's like in time, and then the boundary of that time interval are, it's like the two n times, t0 and t1, and then I define the discrete Lagrangian in terms of the positions at t0 and t1. So this is what we call q0 q1 in the original formulation. So this is the q0 q1. In the field theoretic setting, it's like now you have a space-time domain. You have to look at the boundary of the space-time domain, and you have to specify the field values on the boundary of the space-time domain. So this is what I have here. This exact boundary Lagrangian is defined in terms of these boundary values, and then it's given in terms of this action integral over sort of sections of this configuration bundle which satisfy the boundary conditions and which satisfy the Lagrange equations in the interior. It's sort of the obvious thing, again, in retrospect. Okay, so the next thing you then want is the multisymplectic analog of these kind of equations. And what you do basically is that you have to differentiate this exact boundary Lagrangian with respect to the field values, it's like at a point in the boundary, right? So in the mechanics problem, you vary the data, the position, right, at one of the n times. Now you have to vary the field values at some point in the boundary, all right? And when you compute that, you end up getting essentially a codimension one differential form. But if you introduce a metric in the problem, then you can think of this intuitively as essentially a component of the multi-momentum which is normal to the boundary, okay? And the reason why you need that, right, is that unlike the mechanics case where the tangent bundle, the cotangent bundle are the same dimension, in this field theoretic case, right, when you have the field velocities, they, it's like versus the associated multi-momenta, the dimension of the multi-momenta is n+1 times the dimension of the velocities. And so it's not sufficient to imagine just computing this variation or this partial derivative and saying that's equal to the momentum, which is sort of the obvious thing you might expect. All right, so it actually really has to be this component, it's like in this normal direction. Okay, so in any case, it's like, so this is the expression which you then have to satisfy at every point on the boundary of the space-time domain, and that's the analog of these equations which you have from the mechanics problem. Okay, so the basic idea then is that in order to construct a variational discretization of this, what you want to do is that you would like this discretization of this boundary Lagrangian to be invariant with respect to this lifted action of the gauge symmetry group. And the idea is that if you could do that, then you would have some sort of discrete notion of multi-momentum conservation law. All right? So the upshot of this is that when you use this Ritz construction for the discrete Lagrangian, then what you really need to do is that you need the space of finite dimensional functions, the finite dimensional function space, to satisfy an equivariance property. So imagine you have a function space which is, say, an interpolant, which involves interpolating a bunch of control points. All right? And then you have a group acting on that data. So imagine you had points in space, and they're all being rotated by the same rotation. You want the interpolant which goes through these points to be related to the interpolant which goes through these points by that same rotation. And if you have that property, then you say that this function space or this interpolation method you constructed is group-equivariant. Right? It's not invariant because it transforms as well. All right? So the point is that if you can choose or you can construct group-equivariant spaces, then the associated discrete Lagrangian you get from these Ritz constructions are going to be group-invariant. And then because of Noether's theorem, the discretization is going to satisfy a discrete conservation law. All right? So that's the essential idea. So now it's like, back to the GR application. You need to construct a discretization of a map from a space-time domain to the space of Lorentzian metrics in such a way that this is group equivariant. And so there are sort of two current approaches. This approach due to Philip Gross and Oliver Sanders, it's like called geodesic finite elements. And then there are these sort of other approaches it's like, which are based on generalized polar decompositions. So the basic idea is the following. You have the space of Lorentzian metrics, which is basically just the space of 4x4 symmetric matrices with non-zero determinant and a signature, which is given as follows. And what you want is an interpolant, which has the following properties. So imagine you have some space-time simplex, and you have Lorentzian metric data. It's like at the nodes of this simplex. You want to interpolate into the interior of the simplex with the property that it recovers the data. It's like when you evaluate the interpolant at the nodes. All right, so this is the first condition. So it is an interpolant. The second of which is that this, this extension of the data stays in this space of Lorentzian metric tensors. And the third of which is that when you transform the data, all right, if you transform the data, then the interpolant transforms in the same way as well, which is this group equivariance property. Okay, and here 013 here is this indefinite orthogonal group given as follows. And so let's, sort of lay to rest sort of the most naive thing you could do. Right? The most naive thing you could do, it's like when you interpolate 4x4 matrices, is to do component-wise interpolation. So this is why it doesn't necessarily work. If you have these two sort of 4x4 matrices with the right signature, and you take the average of them component-wise, then you end up with this matrix here, which doesn't have the right signature. So at least in some cases, if you naively component-wise interpolate, it's like Lorentzian metric matrices, which are sort of representatives of Lorentzian metrics, they don't stay in the appropriate space. All right, so this is not the right way to do it. So the other thing you could do, it's like is to do sort of this geodesic finite element construction, which is described in greater detail here. And the basic idea is that you have to endow this space with a Riemannian metric, which it turns out you can. So you can endow the space of Lorentzian metrics with a Riemannian metric. And then you take this weighted sort of combination of the distances, and you sort of minimize this over the space which you're working with, all right? So it's easy to check, it's easy to convince yourself because of the way the problem is set up, it's easy to convince yourself that this is going to be equivariant with respect to isometries of the Riemannian metric structure which you impose at this. But the problem from a computational perspective is that then you have to do a minimization problem on the space of Lorentzian metrics. So that's computationally expensive, all right? So, so our approach is the following. So if we had a Lie group, right, then you probably know that there's an associated Lie algebra to it, which is a linear space. And these two things are related locally by an exponential map. So if you had a Lie group, then the usual way of approaching the problem with interpolation and group equivariant way on a Lie group is to basically take the data, transform it to the Lie algebra, where now you are on a vector space, and then do the interpolation in the usual way, and then exponentiate back to the group, right? So if you could do that, that would be great. Unfortunately, right, this space of Lorentzian metrics is not a Lie group, but it is a symmetric space. And there is an object which is analogous, it's like to the Lie algebra. It's like in the sense that you can construct a local diffeomorphism between, it's like the symmetric space and what is known as a Lie triple system. Okay, so so the way you do this is the following. So you have this space, it's like the space of Lorentzian metrics, and you can characterize it as a symmetric space, sort of as this sort of quotient space in the following way. And the way you sort of do this is to look at this equivalence class of matrices modulo, it's like this orthogonal sort of indefinite orthogonal group element, and the map is given as follows. And you sort of pick, if you will, the right signature by choosing this representative element J, okay? So for every coset that's like in this space, it's like there is a canonical representative because of this generalized polar decomposition which you have here, okay? And then if you look, if you look at the space, it's like Y, and you look at the log of this, these elements, right? Then you end up with what is known as a Lie triple system, okay? Which is given as so. And so the basic idea then is that from this Lie triple system, you can exponentiate it to look into this space, and when you take the equivalence class, you go into this quotient space, and then once you have that quotient space, you can use this identification you have to then map to the space of Lorentzian metrics. So the basic idea is that you can check that all these maps, it's like are are locally well defined. It's like they're invertible. And so you can go from the space of Lorentzian metrics back to the Lie triple system and back again. Okay, and then you can do interpolation. It's like on the Lie triple system, which is a linear space, and interpolation in linear spaces is easy. Okay, so that's the intuition, if you will. So when you actually write all of that out, it's like then this is what you get. This is the interpolation formula. And in order for it to actually be an interpolant, these shape functions, if you will, have to satisfy the Kronecker delta property. Okay? So there are several nice properties about this interpolant. It's like which Evan Golick will say a little bit more about in his talk. But the ones which are relevant for my applications here are that they are signature preserving, so it stays in the right space, and that they have this frame invariance property, which is this group-equivariance property. All right, so you can apply this to interpolation. So this is the Schwarzschild solution. It's like of the Einstein equations. All right, so it's a it's this spherically symmetric vacuum solution to the Einstein equations, all right? And you can check that if you use linear shape functions, then you have the sort of expected rate of convergence. The interpolants, it's like all stay, it's like in the space of Lorentzian metrics. And if you sort of, increase the order of the shape functions, so now you have quadratic shape functions, they sort of increases the order in a natural way as well. All right, so this turns out to be related, it's like to other methods. You can basically, so here it's like there's sort of an implicit choice of base point. If you sort of change that, it's like so that you have the interpolant on both sides. This is sort of an implicit definition of or analog of this equation. If you choose this instead, then it turns out that the interpolant is equivalent to this geodesic finite element construction. And if you replaced this J matrix with the identity matrix, then instead of having interpolants on the space of Lorentzian metrics, you have interpolants on the space of symmetric positive definite matrices, and it recovers sort of a standard result. It's like from the literature. Okay, so you can generalize all of this to symmetric spaces in the following way. I'm not really going to go into details, and my thing is not working. Okay, all right. And so they're sort of an analog of this. And it, again, relies on this idea of this Cartan decomposition of the Lie algebra of the big space into the Lie algebra of a smaller group. It's like, and this Lie triple system. Yeah. All right, so this is the diagram you get. So let me just sort of summarize by saying that gauge field theories exhibit gauge symmetries, and these impose Cauchy initial value constraints, and because of that, they're determined in some appropriate sense. But the point is that they result in degenerate field theories, and you can describe these using multi-Dirac mechanics and multi-Dirac structures. I've talked to some extent about the systematic construction for constructing and analyzing Ritz variational integrators and how one might extend this to the Hamiltonian PDE setting. The sort of main point, or one of the points, is that if you want to construct things which preserve momentum in some good way, then you need to go about constructing group-equivariant finite element spaces. And in the context of general relativity, you can do this on, in particular, Lorentzian metrics. It's like by using a construction which is in some sense based on this generalized polar decomposition. So let me give you a plug. It's like on a new book. It's like we've finished writing. This is primarily on showing that geometric methods can be applied to non-trivial engineering problems. It's really designed for people, it's like from engineering. And then it's like if you're interested in learning more about these interpolants and symmetric spaces, then you should go to Evan Golick's talk. It's like later this afternoon. Thank you.
Thank you very much, Melvin, for this nice talk. And now we can open for questions. Wolfgang.
In your construction of these Ritz integrators,
Right.
you're minimizing this quadratic form that involves a matrix M.
Sure.
And the best approximation property must depend on the condition of that M.
Right.
Does that affect the step size?
Yeah, so it affects how large a step it's like for which this is valid. Yeah, definitely.
So when you did different different.
For different problems, I mean, this analysis.
And this is the main factor in choosing the step size, I guess.
Right, yeah, so it's like an ellipticity element estimate, yeah.
I have a question.
Sure.
Could you comment about the connection between these geodesic finite elements and Regge finite elements?
And
Reggie finite
finite elements? I'm not actually sure what the Reggie finite elements are. Are they the ones which sort of induce Reggie calculus?
Yes.
Okay, all right. So, so my interpretation of Reggie calculus is that, I mean, so of course, Snorri Christensen, it's like has this result, it's like which shows that you can derive Reggie calculus by using this construction which is due to Doug Arnold, it's like which relates finite element exterior calculus, it's like with the sort of elasticity complex basically, right? So you take the elasticity complex and you use this sort of Gelfand resolution, it's like to essentially realize the elasticity complex component-wise as a bunch of Dirac complexes that allows you to then use FEC, it's like to study this. And then in that setting, I think if you use Whitney forms as the lowest order finite elements, then you get the usual Reggie calculus construction. I'm not sure necessarily that's the best way to do it, but that's certainly one possible way to realize this. And so, how does it compare? So for one thing, it's, it doesn't necessarily preserve all these geometric properties. It's like, it certainly stays in the, so let me sort of give you another example. It's like, so, see, it's important to realize that just because you choose the right function spaces, it doesn't mean that if you use sort of a weak Galerkian formulation of it, that you get equations which are well behaved, right? So as an example, we developed in other work a space-time version of Whitney forms, okay? And so that would be probably the natural way of interpreting it directly. And if you did this, you applied this to a simple problem like the 1+1 wave equation, there are two ways to then take the space-time Whitney forms and derive discrete equations, one of which is this variational framework, and the other which is just doing Galerkian projection onto space-time Whitney forms. And so Doug Arnold, it's like, did this, it's like he essentially used Whitney forms, did Galerkian projection of the wave equation, he got results which were unstable, okay? And many years ago, it's like I showed a plot that's like where if you did the same thing but with this variational framework, right, then you end up getting much better stability properties. So I guess the point is that it's not just the approximation spaces which are part of, you know, the magic, if you will, it's also the fact that it is a variational discretization. So, so it's not enough for the approximation spaces to have the right properties, right? It doesn't, so just because, I guess what I'm saying is just because you have these nice approximation spaces doesn't naturally mean that the discretization is going to preserve all the associated conservation laws. So there isn't necessarily a no-fit theorem unless you have this variational construction.
And on the contrary, it's not enough to preserve the conservation laws to converge, right?
Yeah, you need everything, right? So I think it's, yeah, I mean, I think geometric structure preservation in and of itself isn't enough as well. And this is sort of the reason why we did this stuff, is to sort of allow you to leverage this connection of approximation theory, which is at the heart of a lot of numerical analysis, right? And so what the error estimates allow you to show is that you can construct arbitrarily high order methods which are related to, you know, approximation theoretic results. It's like about function spaces. Yeah.
Okay. If there are other questions, now is the time. If not, let us thank the speaker again. And let me give you a little announcement. There is a poster section going on in the garden. Don't miss it. The posters will be different tomorrow, so if you have not seen some of the posters yesterday, this is your chance.